I'll try to move a little fast here to try and catch up to Justine's warning, but please feel free to raise your hand or stop me if you would like me to, or slow down a little bit if there's a need. When I started to read or try to start learning about occupancy, it took me a while to understand what exactly occupancy means. You can interpret it in two different ways. Both of them mean more or less the same thing. One of them is the proportion of area occupied by a species of interest. The other way you can say that the probability that an area, a particular area, is occupied by a species of interest. Now, what they mean, I'm just going to come to the next slides to talk a little more about it, but the key variable here we need to look at, and that's how occupancy is written, and this is the notation we'll be using throughout, is the letter psi, right? Psi, yeah, the letter psi, it's a Greek letter psi, that stands for occupancy. Now, what does proportion of area occupied mean? You might remember the same image Justine showed a while ago. Yes, psi is equal to occupancy. Thank you. Now, let's say we have about 15 sampling units in a study area of our interest. When we go out and do sampling, we end up saying that 8 out of those 15 sampling units were occupied by the species of interest. Let's say in this case it's ibex. So the occupancy estimate that we get is 0.53. You simply divide where a species is present, and you divide it by where all you have surveyed. So if you have surveyed 15 units, out of them you have found the ibex in 8, your average occupancy of ibex in this case is 8 divided by 15, which is 0.53. The only problem, or the point to remember with occupancy, is that it's a size dependent estimator. So probability of occupancy in a sampling unit depends on the size of your sampling unit. Now, I'm just showing you this example that you see in front of us. Same distribution. The distribution of animals is not changing. The only thing now that's changing is the size of my grid. And it doesn't matter. Occupancy theory has no problems if your grids or your sampling units overlap with each other. So don't worry about that element. It's perfectly fine. But in this case, I've just made the size of the grids bigger. I think it's almost double. When I do this estimate, now I'm saying there are 5 out of 7 units which are occupied. So my occupancy estimate for the same distribution has gone up from 0.53 to 0.71. Nothing else has changed. The species is still using the same area. Nothing else is changing. The only thing that changed is my sampling unit, which is why it's extremely important. And just let's go one more example, one more case. Now it's even bigger. Again, as I said, no problem in sampling units being overlapping with each other. But now it's just saying 3 out of 3 sampling units are occupied by the species. So my occupancy estimate is 1. For the same distribution of the species, I have 3 different estimates of occupancy: 0.53, 0.71, and 1. Now it can't go more than 1 because you can't have 4 units out of 3, right? You have to have, at the most, there can be 3 units that you're sampling. Now, the point that I'm trying to drive home here is that any comparison over time, over space, between 2 areas, or in the same area over time, when you're dealing with occupancy, you must keep your sampling unit size constant. The size of your sampling unit, if it changes and you're showing a difference in occupancy estimates, then it's just wrong. It's just not even correct, right? So you have to be very careful of that one element. How big your sampling units have to be, we're just going to come to that in a few minutes. Okay, now Again, 8 out of 15, psi comes to 0.53. Fair enough, straightforward. But the problem is the wilderness or all the habitats are not like a football ground where you can just go and count, or you can just fly over it and just make a quick head count. They're not like our barn where you might have 15 goats walking around and you just calculate them. As Justine showed this map earlier, there is vegetation, there is there are rocks, there are crevices, there are alleys and and canyons where you can't see everything. And more important than anything else, animals have an incredible skill of hiding, of being invisible through camouflage or their behavioral traits. And of course, when you're going in forest areas, 20, 30 meters from you, even if there is a tiger sitting there, you just won't get to see it. So visibility or detectability is a little devil that Justine pointed out. We have to be careful. We have to be addressing it. In this case, for the same number, again, see, this is the original occupancy. This is the true occupancy, right? 8 out of 15 units are occupied, which means my size 0.53. But if I do a count here, I'm actually now saying, no, it's only 0.33, because I could see the animal, the ibex in this case, in only 5 out of 15 units. What has clearly happened is I have underestimated the occupancy. And this is also what we call as naive occupancy estimate. An occupancy estimate, or a probability of a species using a sampling unit or a study area, which does not take into consideration the detection probability, is called as the naive occupancy estimate. We'll be doing a little bit of this later, because naive estimates are a very valuable estimate of showcasing why it is important to do a certain or put a certain amount of effort into estimating occupancy through the methods that we will be talking about, rather than just trying to replicate or repeat the surveys the way they are. Now, so what it basically is showing us is that there is an unknown factor, in this case, P, the detection probability that we've just spoken about, which we are not looking at. And that P is something that we need to calculate. How do we estimate P? Fortunately, Daryl McKenzie, Jim Nichols, and their team came up with almost a groundbreaking modeling process in 2002. And I think I'm not mistaken, it has been cited more than about 2,000 or 3,000 times by now. Not just that, it's one of the most cited papers. It's one of the most widely used and exceedingly diversified in its applications. One of those methods. As recently as a few days ago, I heard that they're using occupancy-based methods to predict where where machine maintenance should be prioritized. Where is it more likely for a certain part or a certain damage to happen in machines, and they're using occupancy-based estimators using maximum likelihood to even predict those. It's a fascinating tool. We'll learn more about it as we go forward. So to address occupancy, what we usually do is the best way or the simplest way to address it is to repeat the survey more than once. And that's one of the basic requirements, and hence the cost implications of occupancy surveys, as opposed to another method where you might just have someone just go into an area once and come back, or just go and look, do a little bit of an effort and come back saying that, okay, there is a species detected, or there is a species not detected. Here, you need to make that little extra effort of repeating the survey. Now, how do we repeat? There is again a way to minimize costs, and it's just coming in a few seconds. But the bottom line is you need to repeat. Let's say F is the unit where I have to go and do the survey. I'll go there. I'll survey F unit once, I'll survey it twice, I'll survey it thrice, maybe 4 times, maybe 10 times, maybe just 2 times. Those details there are guidances towards those. But what we definitely want is each sampling units should be surveyed more than once. How do we do that? We'll come to it. So in this case, what I have done is I've just simulated this little survey. So F, G, D, B, and L have shown presence right now. So if you look here, oh, 1 second, please. You see snow leopard present. You see ibex presence in these units right now, and that's where we have detected the presence of the species. Now, when I do the survey again, the second time, for some reason there was, maybe it was raining or something happened. I just didn't see, or this animal was sleeping. Maybe at that time I couldn't see it there, but it is, the species is there. I only detected in these units, and one of the units where I did not detect it the last time, this time I ended up detecting it. The unit F, you see, this is where the animal is hiding. So that's where I've detected it this time. In the next time, so in B, both the surveys I have detected it. In D, I have detected the species on both occasions. G, I have detected it on both occasions. And L, I have detected on both occasions. H is one of those units where when I went for the first time, I could not see it. But when I went for the second time, I ended up seeing the species. Now, this is an interesting occurrence. There's another interesting occurrence, which is this one, where in the first survey, although I saw the species, in the second survey, I just missed it. Now I go back to the same sampling unit the third time, and this time what I do is, again, for some reason, maybe it's raining, or maybe the animal's sleeping, or maybe the animal's just quietly moved away, or something has happened. This animal's just not visible, right? Now, when I do the third survey, I end up seeing it in some new places where I didn't see them earlier, like J. I hadn't seen it in the first time. Some of the units I have been seeing it every time. So these are, fairly high detection. In L, I see it. In G, I always see it. And that's it. Now, some of them, I've just seen it for the first time. Okay, I've done that. And some of them I have, like in B, I saw it on the first 2 occasions, but the third occasion I missed it, and so on. So you see, there is something happening. And you will notice this happens almost invariably every time, not just because you are a good detector or a poor detector. As a surveyor, you're good or bad, but a matter of chance. Sometimes the animal is at a place where it's visible, or the animal will be right on your path, or or for some reason the animal, like, set up a camera for 10 days. You won't get the animals every day. You'll get on the third day, but that doesn't mean the animal wasn't there on the first, second day, and the fourth and fifth day. So this is exactly what is happening. You're detecting the species in this case on 1, 2, or 3 times. But there's one interesting feature which we will come to in a short while, that there are also some sites where the species is there, but we haven't detected even once. I don't know, I think it's in the next slide. Okay, I'll come back to it. Now, what we do is, now look at this, what I have done. This is the other, so I have surveyed the area 3 times. Now, in some areas, I have detected the species. In some areas, I have not detected the species. All I'm doing is, for wherever I have detected even once, let's say in this one, in H, I've detected it once. So definitely the species is living in that one, right? It's only that on the first and the last occasion, I did not see it. But because the animal is using it, I at least saw it on the second time. J is another interesting case where on the first 2 times I did not see it, but on the third instance, when I went out to survey, I saw it. So yes, it is present, right? If a species is detected in one of these 3 occasions, we can't say that the species is not there. It's there. That's why you see it. If it was not there, then you wouldn't have seen it. So wherever I have seen the animal once, twice, or thrice, I've given it a value of 1. And this is a very simple exercise. You can always, 2 or 3 surveys. You can very easily do it on Excel or anywhere. Just sum it up, and any value which is not 0, call it 1. Any value which is obviously 0, let it be 0. And this gives me another naive estimate. So all I'm doing is I'm counting 1, 2, 3, 4, 5, 6, 7. I'm calling it 7 out of 15 sites are occupied. Now, if you look carefully, you'll notice that it is definitely more than what was the case in the first case, in only surveying the site once. I was saying only 0.33 was the occupancy, but by repeating the survey, just by repeating the survey, my occupancy has gone a little bit up. But is this still the right estimate? Actually, no. We still call this a naive occupancy estimate because we are not addressing the detection probability. What do I mean by that? Isn't there a possibility? Now, given the chance, like look at this. What if I did not conduct the third survey? What if I had stopped just after 2? I would have called J as absent, right? Which means just by chance, because I did 3 surveys, I ended up detecting the animal of interest in the third survey, right? Similarly, could there be another site where the animal is there, but I've by chance not seen it? Maybe it is in C, maybe it is in A, maybe it is in M or N. Maybe it's there, but I'm not seeing it. And that is the problem that we are trying to address. And to both Rub and Annalise's questions, I'll come to exactly try and explain how many repeats you need to do. This is still not the occupancy estimate we are interested in. This is still naive estimate. This is a simple number of the sampling units where all I have done is I've increased my effort. Instead of spending let's say each survey takes 1 hour. Instead of doing 1 hour survey, I'm doing 3 hour survey. Obviously, if I'm sitting in an area for a longer time, I might have a greater chance of encountering the animal, right? So all I have done is I've increased my effort. Instead of 1 hour, I've done it 3 hours, but nothing else has changed. It is still a naive occupancy estimate because there is a very strong possibility that some animals are there and I never got to see them even after 3 hours, spending 3 hours or spending 3 trips or spending or doing 3 different little transits or whatever, right? Despite 3 efforts, repeated efforts, I am very likely to not see a species despite its presence. And it's being shown us by these cases. See, I could have very easily just, actually this is the 2 cases. 2 cases where it's a matter of chance that I ended up seeing the species where in one of those surveys where I could have very easily missed them. And we need to be, and that's why I'm saying that there is a possibility that maybe A has a species and I've just not seen it. And I'll show you in a second what is actually happening. Now let's go to the next slide. There, yep, A. Now A actually has ibex. If you look carefully, no, it doesn't have it. Sorry. Okay. Yeah, what's happening here? Now there are 4 different scenarios we're going to look at. Scenario A, what are the 2 possibilities? Possibility 1 is that species is absent, right? Now, if a species is absent in A, there is no way I will detect it, right? So P, there's no point of talking about P. If psi is 0, then we don't even worry about P. The other possibility is that there is a certain that the species is using it, but I have not seen the species with a probability of 1 minus P. Now, P is probability. So probability of getting a probability is always sums up to 1. So let's say if I have a coin, the probability of getting heads is 0.5. This is probability of getting head. Probability of getting tail is 0.5. If I have a biased coin, then probability of getting head would be 0.7, let's say. What would be the probability of getting tail? It will be 1 minus 0.7, which will be 0.3, right? So that's a simple example of what probability does. All we are saying here is that the probability of detecting a species is P. Oops. Sorry, of detecting a species is P, then probability of not detecting is 1 minus P. So in case of A, when I did the survey 3 times, in each time, there is a possibility that the species just wasn't there, in which case I won't see it, so I don't care about it. But there is a possibility that the species is there, and I missed it on the first occasion, and I missed it on the second occasion, and I missed it on the third occasion. Oops, 1 minus P3, right? Now, this is a possibility that can happen, that even though the species was there, I did not see it on the first, second, or third instance, right? That's a possibility. The other possibility here is that the species is not present. So which would be just simply 1 minus psi. So there are two possibilities. Either it's this, or it's just species is not present by a probability of 1 minus psi. Probability of a species being in the cell A is psi, and probability of a species being absent from A is 1 minus psi. Everything is being dealt with in probabilistic terms here, right? So that's what we are sort of, one second. Okay, now let me take you to the other example of what's happening in this case. This is the case of M. Now, what is happening in case of M? When I went there for the first time, I saw the species with a probability, and okay, because it is detected at least once, I definitely know that the species is present. Why am I showing M and H here? I think I missed one of those. Okay, let's say, forget about this one. I'm actually showing H1. Yeah, this is the one we are talking about. Sorry, I missed it there. Now, psi, so the likelihood of this particular case being true is that psi is there. I mean, the species is present there, but I missed it on the first occasion. Then I detected it on the second occasion with the probability P2. And then I missed seeing it on the third one with the probability 1 minus P3. Species is there because it was detected at least once. That means we are 100% sure now that species is using the grid cell H. All that is happening is I haven't seen it on the first and the third occasion, right? And if I know, if there is a way I can find out P, then I can start predicting how my estimators would be. I'll just show you another example. In case of L, now what is happening in this case? In this case, I know for sure the species is using the sampling unit with a certain probability, and I'm detecting it on the first occasion, and I'm detecting it on the second occasion, and I'm detecting it on the third occasion as well. Now, this is the likelihood of this particular scenario being true. Now, this is the third scenario. Now, similarly, I have one more case, I think. Yes, now this one. Now, this is the most interesting part, which is exactly what's happening in the first part. And I can show you slightly more complicatedly here. But if you remember the scenario LA, likelihood of the, oops. Likelihood of the first capture or detection history being true is there are two elements to it. One element is that the species is present and I have not detected it with 1 minus PA1, 1 minus PA2, and 1 minus PA3 probabilities. Or possibility two is that the species itself is absent in that unit. The probability of a species not being there in a certain unit is 1 minus psi A. Situation 2, LM. Am I doing M or H? This one is, this is this one. Okay, that's correct. This is LM. Again, exactly as the above, because now the difference between these two is in one of them, I know for sure that the species was present. If you look back, in M, we have the ibex. It's just that we've not detected it. So in reality, although this is what it's predicting, I know that this is not true. I know this is true because I know the reality or the truth in this case. The point which we are saying is that this, in a real life scenario, we will never know whether it's case one or case two, whether we have the species and yet it's not seen, or we simply don't have the species. And that's where we get into the whole realm of likelihood estimation, where we have more than one unknowns in an equation, and we use the maximum likelihood to find the most probable value for psi and p, the two unknowns in this case, to fit this particular data. Third case, I'll quickly go through it and then we'll come back. Now, in this case, what is happening is in case of H, if you look carefully, this one, I am seeing the species on the first, on one of the occasions. So I know definitely it's there, but I didn't see it on the first occasion. I saw it on the second occasion and I didn't see it on the third occasion with these particular probabilities. 1 minus pH1 is the probability of not detecting the species on the first survey. pH2 is the probability of detecting the species in the second survey. And 1 minus pH3 is the probability of not detecting species on the third survey. And this is one we've just discussed. It's a case where you see it every time. So you know definitely it's there and you're detecting it with a certain probability. Now, all of these are unknowns, but there are some generalizations that can be made. We can start assuming that PA, probability of detection, is constant across the entire study area, or it is variable across the entire study area. We can use all of these as unknowns and use likelihood estimators to come up with the most probable value for a psi and a p that will fit here. In other words, what we do is we use this, all of those likelihood canonical equations that we've just discussed. They can be put together in a simple likelihood equation, which can then be solved. And you can do this on Excel if you want to. And if some of you are interested, I'll happily share with you a simple Excel exercise to do this and come up with the likelihood of the probability of the species of our interest living in this study area. Yes, Nilofer, I'll definitely send you the Excel to do that. Okay, so that's what we essentially do in occupancy estimation. We survey a site more than once so that we have data on which can tell us something about the probability of detection, which is not 1, it is less than 1. If it was 1, then we would detect everything. But because it's less than 1, we have to find a way to estimate it. So when we survey a study area more than once, we collect data, which is then backfitted to the likelihood estimator, and it tries to find the best possible estimate for which my value of psi and p are estimated. And those are the values which we report. And in the next session, we will do a simple exercise where we will estimate it, and we'll see how close or not so close we are to the actual value. And looking at the way maximum likelihood works, it's almost like magical, because it's just fascinating how close to reality it gets us, using an equation where we have two unknowns. And it's almost like we have unknowns on both left side of the equation and the right side of equation, but it just finds the right balance where they're giving us the best possible solution. Okay, now quickly moving to, okay, Justine, so that's where I would stop with the broad explanation of occupancy. What we can do is, I have another few slides. We can either get into the details of how do we do surveys, or we can take this in the next session, what exactly we mean by surveys. So let me know what others think. We can, or we can take questions right now. What would people prefer?
I think I would suggest take a few questions, Kustub. I tried to answer some, and thank you to Chloe for also helping answer some questions. And then we can go into it next time, because it's building on it, right?
Yes.
And it can be, because I think there's already a lot, I'm sure, that's people that are new to Occupancy.
Sure. So let's get going from Occupancy. Okay. Nilofer, Helena, for occupancy and sampling unit sizes, it seems very hard for highly mountainous topology, given variation of vertical gain per unit of survey. I wonder there's some aspect of algorithm. Yes, so Helena, and we will talk about this, that what defines a sampling unit. We definitely seek some sort of a homogeneity, but if there is a mountain here and there's another mountain here, if both of them have similar characteristics, even if the variation in altitude is like, from 2000 meter to 6000 here and 2300 to 5800 here, they're still very similar. They're still homogeneous in their being mountainous, right? So I think the variation in altitude is not that much of a challenge, as long as we can seek some sort of a homogeneity within the sampling unit. And how we can do that, we'll come to that when we get to the next section. Okay, Justin, you've already responded, sorry. Is it worth to continue surveys until you reach maximum detection? So Rab, the beauty of occupancy surveys is, no, you don't need to. You can do, in some cases, just do 2 or 3 surveys. In some cases, you might need to do 10 surveys. And even there, what is a survey? It varies. In some cases, it's you can walk a transect, right? So 500 meters, another 500 meter, another 500 meters. So each 500 meter segment becomes a survey. So you can do an entire grid in just one big survey, where you are making several replicates or several spatial elements. If you have 3 people, send the 3 people to 3 different surveys. They happen at the same time. So there are guidance on what is the optimal number of replicates given what your expected detection probability is. So if you have, so typically what we do is we do a pilot, and we come back with some idea of, okay, it's going to be difficult to spot snow leopards even though they're there. So we will have some estimates, and you can run it on the present software or in our presence, and it'll give you some estimate that, okay, your psi would be, let's say, 0.3, and your detection probability will be 0.1. Given these two, how much effort you need to put? There are guidance, and they're very simple, straightforward, literally algebraic equations, which you can plug those numbers in, and it'll tell you how many sites you will need to survey to get the optimal data with the expected or the desired level of confidence intervals, and how many times you need to replicate. So in very simple words, there's one simple, I think, a rule of thumb. If your animal of your interest is very sporadic, like, it's using, let's say, in an entire mountain range, there are only 4 or 5 little pockets where the animal is found, then you need to increase the number of your sites. But if your animal is fairly distributed and it's very difficult to see, then you need to increase the number of replicates. So there's a kind of a balance that you draw between the two. And again, guidance for those is very easily available. We will be showing an equation. I think thank you, Justin, for stopping me here, but we do have that equation coming in later in the same presentation, where we'll be looking at how do you decide that.
Can I add just to that is Rab, so I think it's related to sample size, and in occupancy there are different levels where you can increase sample size, different ways you can do that. But in terms of your replicates, but because we're estimating probability of a number of species, you do want that probability to be more precise. So if you do only have like 1 or 2 surveys in all of your sites, that might not be enough for your survey if they're very hard to detect. And your variance might be very high for your occupancy, right? And for your covariates. So in those cases, you might want to do many more repeats, but there's maybe not the need to do maximum number. And like Kustub said, you can get an estimate of what this might be. But the estimate using the equation Kustub might share later might suggest you do like 200 sites and this many repeats, and it's very unrealistic. But then you can go back and say, okay, but I have this much money, I can do this much. Is that still reasonable? Can I still go out and get a reliable, a precise estimate? But yeah.
So as Justine said, the cost you will pay for not doing those many surveys is slight increase in your variance, for example. And if you and your manager and your end user is okay with that level of uncertainty, it's fair enough. So so these are a few like the multidimensional decisions one has to make based on these 2 or 3 unknowns. But that kind of a guidance is available, and I think it becomes very useful to be able to plan ahead rather than be surprised with it towards the end of the survey. So which is why pilots become extremely valuable. Okay, so Luciano, I think you also had the same question. How do we know it is the maximum? As I said, we will get to know what's an optimal number of replicates once you have some data and you know what your desired level of error is, right? So you can do that through those. Nilofer, yes, Nilofer, using interview-based data is also a very useful and a very effective method to collect replicates. In other words, you remember I mentioned the example of a mouse in my office. Now someone comes and asks me, have you seen mouse in this room? I say, no, I haven't seen a mouse in my room. Someone goes and asks my colleague, Venera, she says, of course there is a mouse. I see it every day. And because, she's probably more interested in the mouse's presence because she's more careful about the office stationery. She has seen it. And then someone also goes to a third colleague of mine and asks, and no, I haven't seen. The 3 observers become the 3 replicates. Yes, I spend less time, she spends more time, could be a variable. My responsibilities are different than hers, could be a variable which might affect me being better at detecting or worse at detecting a mouse than a Venera being more effective at detecting a mouse. So those are there, but yes, Nilofer, you're very right. We can, how you create a replicate, it's extremely flexible. And we'll talk about this a little later as well. It's less accurate compared to camera trapping or genetic, but yeah, I agree, Nilofer. I think we ourselves have 2 papers out of this work on snow leopard distributions, one in south of Kyrgyzstan and one in a state in India, where we've used the same interview-based methods. And they're fairly accurate because in one area right now, camera trapping has gone on, and it has sort of aligned fairly well with the assumptions.
Can I just add also interview-based, you can look at change because people might have information on the past, while doing signs, surveys, or cameras is really about the present.
Absolutely, absolutely. How many time do we need between each survey? Minimum, maximum. Your surveys can be continuous, Annalise. They can be literally one long transect of 5 kilometers can be split into 5 1-kilometer segments, and each of that 1-kilometer segment can be treated as a replicate without a problem. You can have a camera trap set for 3 months, and depending on what's the most optimal value of detecting a snow leopard, let's say in a month or in 10 days or in 15 days, you can have 3 or 9 replicates. So that's another way of looking at it. So it's again extremely flexible. You can have, there's no necessity how much dependence, how much time separation or how much spatial separation should be there. There are models which are available where you can address this a possible correlation. You know, if I'm seeing, let's say if someone's working on leopards or tigers, you might know leopards and tigers work on tracks, on roads or trails. Now, if you're doing a transect on those trails, that you see a tiger footprint here, you're very likely to see it in the next segment because you're just dividing the same segment, and maybe the same tiger has moved into 3 or 4 segments. So there is a spatial correlation between the segments. So the chances that I have seen a tiger's footprint in a particular sampling replicate are very high if I have seen it in the previous one, and they're very low if I have not seen it in the previous one, right? So there's a dependence, there is a relationship between them, there's a correlation between them. Those correlations can be addressed very cleverly and very effectively using Markov chain models, I think, and they really are not a problem. So it's extremely flexible. The entire methodology has been developed so much that it's quite flexible on some of these violations of assumptions.
Yeah, that can I just add a little bit, Kustup, just to add that often the simple model assumes one assumption that I think Kustup will share next time we'll share is a closed population estimate, right? Is like SCR, it's closed. So you no extinction, you know, we don't actually want the animals emigrating out of the area or new ones coming into the area. So if you are trying to do occupancy with camera traps, you might not want to be doing it for a whole year, for example, and then dividing that in a whole year, because there might be risk of individuals leaving if you assume this closed population. But there are also open models. So that might help inform you how often you do, when you need to come, or the time between repeats, right, Kustup? I mean, that is an
Absolutely. Absolutely.
For repetitions.
Yes. And we'll come to this in slightly greater detail of what are the costs, or what's the trade-off of violating these assumptions. And you'll find it fascinating that in some cases, just the way you interpret your results, that it makes it fine to have those assumptions being violated. But we'll talk about those, and please be assured we'll be discussing those in greater detail. Then we have another question. Muhammad Abu Bakr is asking, for finding the occupancy, we have to survey in all grids of its home range? No. Again, I'm sorry, all the questions, I promise we will deal with all of these, but the beauty of occupancy-based surveys is that you don't need to survey every nook and corner. You can sample within samples, right? So occupancy method allows you to sample your sampling as well, and it's absolutely doable. You don't need to survey every nook and corner of the grid cell. Yes, sorry, Justine.
But just to clarify, if you do want to extrapolate to areas you didn't survey, you need to plan for that. Yeah. And that can be done either by covariates, or you assume that they're the same as your current survey. You know, it's for extrapolation to non-surveyed areas. There are ways to do that, but it's good to plan and in order to collect data in the areas you do go to be able to do that. But I think we'll talk about that with covariates and things later.
Yes, Letro, we will provide you with not just an R script to run an analysis, but also how to organize your data. And Muzaffar, who's with us here, and yeah, there he is. So he'll also be able to help us explain how we've used some of those, some of his data, which was actually an interview-based survey, and how do we translate that data using a simple script into occupancy compliant data set. So we will definitely be giving you an entire R script, an annotated R script. So that's part of what we will be doing towards the end.